Bam. And here's what we can do very quickly. Here's actually, if you're watching this at home, I don't know if this would be enough, but you can pause it as we go. Here's all the solutions. Right there. And then if some of this doesn't make sense, then you can just fast forward and listen to me ramble on about it. There we go. And let's see, a couple more slides. Yep, that's all that. And I think that's the last one. All right, let's clear this out and let's do it. Today and tomorrow we're going to do kind of a comprehensive or review of polar. So today and tomorrow's very quick review of that polar chapter that you did in Honors Pre-Calc. Then we'll get into the calculus of it. So we won't do any calculus today, no calculus tomorrow. Polar coordinate system is a plane with a point O, the pole, and a ray from O, the polar axis. Each point P in the plane is assigned polar coordinates as follows. R is the directed distance, or the magnitude from O to P, and theta is the directed angle whose initial side is on the polar axis and whose terminal side is on the line OP. So, in other words, we have a certain length that we go from the pole. This is O, that's the pole. This is a certain length, and we call it R. We call it R because it's really the radius of that circle. So we have a certain circle that we're on, and we can't pinpoint that point until we say, well, we're on that circle. It could be anywhere on the circle, but once we say the angle on that circle, once we say theta, now A is a unique point. There's no other point that has that R and theta combination. And it's always R and theta. So it goes the radius and then the angle. So once you give R in that angle, you got a unique point. However, if we have an opposite R, if we go down here and go, well, this is negative R down here, and it's off the board, of course, and then give the angle to that one that goes all the way around, then we can go to this angle and then go in the opposite direction and be at the same point. So there's some negative R with a theta that would give the exact same point. So every coordinate is a unique point, but you could have multiple coordinates for the same point. Plot the points with the given polar coordinates, 2 and pi over 3. So 1, 2. So it's on a circle with radius 2, and then once you say it's pi over 3, that pinpoints that point. But we could say that it's 2 comma, instead of going pi over 3, we could go the other direction and go there's 3/3, 4/3, 5/3, negative 5 pi over 3. Now this is a unique point and this is a unique point, but you can have different coordinates for that unique point. We're on a radius of 2 for letter B. And we're kind of at 3 pi over 4, but it says go back to, go the other direction. So that puts Q down there. So go along that angle, but go in the opposite direction. That's what a negative R would mean. And then this one, we're on a radius of 3, like that, and at negative 45 degrees. So that puts us about right there. There's negative 45. So that'd be point R down there. Each polar coordinate pair determines a unique point. However, the polar coordinates of a point P in the plane are not unique. So let's go down to the exercise. If the point P has polar coordinates 3 pi over 3, find 3 additional pairs of polar coordinates for P. Now, there's an infinite amount of points because we can just keep going around and around and around and around the circle. But if we just talk about from negative 2 pi to 2 pi, we have 3 and pi over 3. 1, 2, 3. There's 3 pi over 3. We should be able to have another positive R. We should have a negative R and another one with a negative R. So we can go forward to 3, and we can go 1, 2, 3. We can go backwards to 3. We can go this direction. So 3/3, 4/3, 5/3, negative 5 pi over 3. That would be the exact same point. Well, now what if we go to this point here, but then call it negative so that it actually backs us up to this point? Now we can go forward to this one, and we can go backwards to this one. So if we go forward to negative 3, that's 3 pi over 3, 4 pi over 3. So go to 4 pi over 3, but then go backwards, gets us to that same point. Well, we can go backwards to this, 1, 2, 3, as far as the angle. So we can go backwards to it and then go negative, and that puts us up there. Negative 1/3, negative 2/3. And that's all of them between negative 2 pi and 2 pi. Now you can get more of them if you go past, you just keep going around the circle, you can get a whole bunch of them, right? We use both polar coordinates and Cartesian coordinates. The pole is the origin and the polar axis is the positive x-axis. By applying trigonometry, we can find equations that relate the polar coordinates and the rectangular coordinates of a point P. Let the point P have polar coordinates r, theta, and rectangular coordinates x, y. This is your toolbox right here. So x is the same as r cosine. Y is the same as sine. So let's say your radius was 1. Let's say you're on the unit circle. It says x is cosine. Well, yeah, x is the cosine, y is the sine. Now, if you're off the unit circle, no problem. If you're on a circle radius 2, we just take 2 times cosine. That's what's nice about the unit circle. We don't have to learn about a whole bunch of different radii. You learn about the unit circle, you got them all. No problem, just multiply. This is the fact that we can take any point, unless it's horizontal or vertical, and we can turn it into a right triangle. So if I knew the x-coordinate and the y-coordinate, then to find the radius, I would just use the Pythagorean theorem. So r squared is x squared plus y squared, right? Square root it, well, and then you square root and all that good stuff. So that's where that comes from. Not only that, if we wanted to find the angle of this, we know that the tangent of the angle is y over x. It's y over x. So how do you find theta? You do inverse tangent. So tangent of theta is y over x. If you want to find the angle, you do the inverse tangent. These relationships allow us to convert from one coordinate system to the other. Example 3, find the rectangular coordinates of the points with the given polar coordinates. So it's 3 cosine of 5 pi over 6 and 3 sine of 5 pi over 6. Now we just have to know where 5 pi over 6 is. Well, that's right there. So it's negative square root of 3 over 2 and 1/2. So 3 times negative 3 over 2 and 3 times 1/2. Oh, I need square root of 3, not negative 3, have square root of 3. So not much you can do with that. And that would just be, of course, 3/2. So here we have 2 cosine of negative 225 and 2 sine of negative 225. So we got to find negative 225. Well, here's negative 180, and another 45 is negative 225. But we're not on the unit circle. We're on a radius of 2, so just multiply. No problem. So 2 times negative square root of 2 over 2, and 2 times square root of 2 over 2. So the 2's cancel. Negative square root of 2, square root of 2. So we use the tools. We use these two right here to convert. When converting rectangular coordinates to polar coordinates, we must remember that there are infinitely many possible polar coordinate pairs. In example 4, we report 2 of those, not TO, but TW. 2 of the possibilities Find two polar coordinate pairs for the points with given rectangular coordinates. This is rectangular. Well, now we're at negative 1, 1. We're right there. So there's the angle. Let's go. We need r theta. So r squared is x squared. And I'm writing everything out. So r squared is 2. R is plus or minus the square root of 2. And it could be positive or negative depending on what angle you want. So let's go 2 comma. And then we would go, I know that's one of the pi over 4s, but to find the theta, theta equals inverse tangent of 1 over negative 1. Well, the inverse tangent of negative 1 is negative pi over 4. It's actually down here. That's what your calculator would tell you because it's the principal quadrants. But we know that if I use 2, I'm not down in the fourth quadrant. I'm over here in the second quadrant. So that's 3 pi over 4. If you go negative 2, then we can use negative pi over 4 because we're going negative pi over 4 and then in the opposite direction. So that's a possibility. So there's two coordinates for that unique point. Now if we're on an axis, 1, 2, 3, 0 degrees or 0 radians. Oh, no, that's rectangular, excuse me. Then for the polar, it's 3. But like this is the one where it'd be either 0 degrees, or if you had 3, 0, it would look exactly the same, but this is an x and a y, and this is an r and a theta. But it depends on the context of the problem. And there's never been a problem in this chapter where there's confusion as to whether it's rectangular or polar. So that's really never an issue. But it could look exactly the same. Convert the polar equation to rectangular form and identify the graph. Well, on letter A, we deal with sines and cosines. We deal with sines and cosines. We don't see any secants or cosecants. So I'm going to change this to negative 2 over sine of theta. And then multiply over the sine. R sine of theta is equal to negative 2. And so r sine is y if you look in that little box. Well, that's a line. And more specifically, it's a horizontal line. Now in letter B, it looks almost exactly the same, except it's already a cosine. We already have what we want. We want sines and cosines, but if I divide the cosine over, that's not going to work. So letter A and B's techniques are different. Here I wanted to get sine over the other side. We can do that. We can't do that here. It's already cosine. So here we're going to multiply both sides by r. Now notice I didn't multiply these by r because that wouldn't do me any good. It wouldn't say r sine or r cosine if I multiplied. But over there, that's what we have to do. And some students try to apply it to both of these. That's not the case. They're completely different, even though they look very similar. All right, this is x squared plus y squared, and this is negative 4x. I mean, look at the chart, the little box I gave you. That's the conversion. But a multiple choice won't have this as an answer, because this is a circle, but that's not how we leave circles. We add the 4x over, and we complete the square. So we add the 4x over, complete the square on the x, complete the square on the y, but the y already is a perfect square. So 4 divided by 2 is 2, 2 squared is 4. So x plus 2 squared plus y squared is equal to 4. Now that's a circle with center negative 2, 0, and a radius of, not 0, radius of 2. Now it doesn't ask you to do this. I realize that. But we're not doing, you're not going to be tested over this stuff. You're going to be tested over this stuff in the context of calculus. So I'm going to show you a little bit more here. The center is negative 2, 0, right there, with a radius of 2. So here, up here, 2, and down here. So it should be this nice, perfect circle right there. That's what we're claiming. we're claiming this in polar is this in rectangular. So if we switch this to polar, right there, we get y equals -4 cosine of theta. And if we go zoom 6, it's exactly where we are, right? To the left. That's the same circle. But I want to ask you a question. Is cosine the x or the y on the unit circle? It's the x, isn't it? And which way, if I had a circle right down the middle, which way was that circle pushed? To the left, right, along the x-axis and in the negative direction. -4 cosine. Negative direction along the x. Notice that the diameter is 4. The diameter is 4. Okay, so could you draw this circle quickly? 4 sine of theta. Maybe you can't. Maybe you didn't get it. Could you draw that circle without, just right now? Maybe you can, maybe you can't. I gave you some clues. One, two, three, four, right there, up 2, hit 2, 2, 2, and it looks like that, right? Because sine is the y. So it takes that circle that's right down the middle and pushes it up along the y, the positive y. The goal here eventually is just to be able to look at this and be able to just graph it. That's where we're headed. But we're taking baby steps because we need to. We need to. This is a chapter in Honors Pre-Calc that you only do once and that's it, and then you're done. Convert the rectangular equation to polar form. X equals 5. Well, x is r cosine. And we don't usually, we want these to say r equals, by the way. So r is equal to 5 over cosine. So r equals 5 secant. So we kind of did, I'll go back to this. We did this one in reverse. We did that in reverse. Right there. This is 3r cosine plus 4r sine equals 8. You can factor an r out. So r is equal to 8 over 3 cosine of theta plus 4 sine theta. Which I'm amazed by this, I really am. Because sine and cosine on the unit circle graphs circularly. Like if we just saw that. If you have negative cosine, it graphs in a circle. And we can graph a line by going around the unit circle with values. So we have 0 and then pi over 6 and pi over 4 and pi over 3. We can plot those points and they're linear. I think that's pretty cool. 8 divided by, now it goes really fast, but I want you to notice how it graphs this. Prepare to not be amazed, but I am. I'm amazed by this. Ready? You gotta watch it real quick. Watch how it graphs it. Do you see that? It kind of shoots up there and then comes back that way. Well, that's because it's plotting as you go around the circle. So as you go around this way, it's plotting these points like this. As you come around here, it goes out here. And then as it gets around, it comes back. Because you're plotting the points in a circular fashion. You're getting the r values from a circle. And then you plot the angles. So that's how it ends up plotting as you go around the circle. And it ends up being a line. Yeah. Polar? Polar. Yep. That's why we're getting, that's why we're getting those thetas. All right. This is now, of course, a circle. But how are we going to get this to have r's and cosines? Well, we're going to multiply it out. X squared minus 2x plus 1. Y squared plus 8x plus 16 is equal to 17. Minus 1 minus 16, that's why we've set it equal to 17, so it kind of works out nice. But this ends up being, well, let's write it like this. Now, this is really x squared plus y squared, even if they're not together. We can put them together. Then minus 2x plus, oh, that should be a y, not an x, plus 8y is equal to 0. This is said to be equal to r squared minus 2r cosine plus 8r sine is equal to 0. Now I need this to say r equals, which looks like it's quite daunting, but we're just going to get these two to the other side and divide by r. So r squared is 2r cosine minus 8r sine, and then just divide by r. Minus 8 sine. Great, right? So what? So here's the claim. This is a circle with center 1, negative 4. 1, 2, 3, 4. Down there. And a radius of square root of 17, which is just slightly above 4. Square root of 16 is 4. So 1, 2, 3, 4. A little bit above there. 1, 2, 3, 4. A little past that. 1, 2, 3, 4. 1, 2, 3, 4. Something like this, very roughly. So that's what I'm claiming. If I graph this, I get that also. We're saying it's the same thing because we convert it over. And I'm not going to do this 100 times. I just want to show you a couple times. Just to show you that they're the same. I want to convince you. Zoom 6. Should be the exact same circle. And it is. There it is. Same thing. Students will be able to convert between rectangular and polar coordinates. Exercise 1 and 2. Plot each point with the given polar coordinates and find the corresponding rectangular. These are polar. So negative 3, but 5 pi over 6. So we're going to go 5 pi over 6, but we're going to go backwards. 1, 2, 3. So this is point A right there. So now let's go negative 3 cosine of 5 pi over 6 and negative 3 sine of 5 pi over 6. But we're using 5 pi over 6. We're using this up here, which is on the unit circle is negative square root of 3 over 2, 1/2. So look, when you take a negative times a negative, you get a positive x value. And then when you take a negative times a positive, you get a negative value. So it's 3 square root of 3 over 2 and negative 3/2. So that's why with a negative r, it reverses these. So now you're going in the other direction. It reverses the signs. So now you're going in the other direction. See how it all works out? I love it. B, 5, an inverse tangent of 4/3. Well, inverse tangent of 4/3 is some angle, some decimal angle. It's not a nice one, but it is an angle. So if I go over to, this is the y, this is the x, because it's y over x. So if I go 3 over, 1, 2, 3, and we go up 4, so if I go up this way and kind of over this way, you know, it's close to pi over 3, but it's not pi over 3. Now that puts you on a circle of 5 units, a radius of 5, where this is 3 and this is 4. So I know that it's 3, 4. It tells me what the x and the y are. Letter C, -1, but 7 pi. Well, pi is 1 pi, and then if you go all the way around, it's 3 pi, and then it's 5 pi, and then it's 7 pi. So over at pi is 7 pi, but then back 1 would be right here. So this is point C. This was point B. It's 1, 0, isn't it? We can do -1 cosine of 7 pi and -1 times sine of 7 pi, but it's the point 1, 0. D. 2 square root of 3. About 3.5. But the angle is 3.5 and 2 pi over 3. So 1, 2, 3.5. Somewhere right there. So now we have 2 square root of 3 cosine of 2 pi over 3 and 2 square root of 3 sine of 2 pi over 3. Cosine of 2 pi over 3 is -1/2, so 2 times -1/2, and oh, that's square root of 3, and then 2 square root of 3 times square root of 3 over 2. So negative square root of 3, and let's see, the 2's cancel out, 3. So this y coordinate, that's fairly close. I'm a little off. I'm probably a little high, but that's close to 3. So I'm fairly confident I got that right. So that's letter D. So some different techniques. We got inverse tangent on this one right there. We're on an axis for that one. I love it when we're on an axis. That makes those really simple. Plot each point with the given rectangular coordinates and find 2 sets of corresponding polar coordinates. So A is negative square root of 3. That's like 1.7, I think. Square root of 3. 1.7, so negative 1.7 and -1. So about right there. Boy, that sure looks like one of the pi over 6s. So letter A, we have, if I square the square root, 3 plus 1 is 4. Let's do this. R squared is equal to negative square root of 3 squared plus -1 squared. So R squared is equal to 4. So R is equal to plus or minus 2, depending on what angle you're going to pick. So if I say I'll pick the positive, then we want inverse tangent of -1 over negative square root of 3. So inverse tangent of 1 over square root of 3, but trig functions are ratios. So this could be 1/2 over square root of 3 over 2. In other words, the y is square root of 3 over 2, and the x is 1/2. Well, that puts us at pi over 6. But we're over here. We're there. So that would be 7 pi over 6. That's where we're at. But it asks for 2 of them. So I can go 2, and instead of going in the positive direction to get there, we can go in the negative direction, which is -5 pi over 6. Three, 4. 1, 2, 3, 1, 2, 3, 4. I think we just did this one. There's the point. So letter B is the point, let's see, 5, right? 9 plus 16 square root of 25 is 5. And then the angle is the inverse tangent of y over x. It's some decimal value. It's around 60 degrees. It's just less than 60 degrees. Here, I'll show you. That's what I'm thinking it is by graphing it earlier. Mode, let's go. Sometimes we think, when it's not a nice, sometimes we think better in degrees, believe it or not. So inverse tangent of 4/3. 53. It's somewhere around 60. I knew it was short of 60. Just didn't know quite how much. 0, -2. Well, I could go through all the mathematic gymnastics, but isn't it the point? Let's go with 2 and 2. Well, you could do 270 degrees. That's okay. That's legal in Nebraska. But I usually do stuff in radians. I'm a big radian fan. And we can go backwards to this as well. So we go 2 -pi/2. There's another one. You want to go -2 pi/2. So you go pi/2, but then you go negative. That gets you to that point as well. All right, let's do the last one real quick. 2, 0. Well, that would be 2, 0 as an angle because it's 0 degrees or 0 radians. It looks exactly the same, but it's different. How about 2 and 2 pi? Same thing. Use analytic methods to replace the polar equation by the equivalent Cartesian. Then identify or describe the graph without using a grapher. Is this our last page? It's our last page. How are we doing on time? If you're watching this at home, you can fast forward through some of this. Try the first one. We got some time here. This one, we have to multiply r on both sides. So that's x squared plus y squared is equal to 6x. But we have to, this is a conic. This is how we deal with conics. We got to subtract that over, complete the square. So we're going to add 9. X minus 3 squared plus y squared is equal to 9. So that's a circle. But here's where we're headed with this. This is x. 1, 2, 3, 4, 5, 6. So it has, there's the center, 3, 0, right? 3, 0, with a radius of 3. So that's what we're trying to accomplish there. Cosine's the x, so it's going to push it along the positive x axis. 2 over cosine. This is a different technique. This is not multiplying by r on both sides because r secant doesn't mean anything to us. We're going to multiply by cosine. I think this is much easier, but this is the one that students tend to forget. Because your instinct is to multiply by r on both sides for some reason. But there's a time and a place for that. All right, this one is x squared plus y squared is equal to -8x. So we fast forwarded by multiplying by r already on this one. So x squared plus 8x, not y. Why did I write y? X squared plus 8x plus something plus y squared is equal to 0 plus something. 8 divided by 2 is 4. 4 squared is 16. X plus 4 squared plus y squared is equal to 16. Circle. This one we're going to multiply by the denominator. And when you distribute the r's, we already have what we wanted, what we want. We want r sine, and we want r cosine. That's what we're looking for when we do these. So this is that one I showed you where it's a line. So we have y plus 4x is equal to 10. Forget about the last one. The last one's very strange. Is that it?